All right, so here's our air drag example. We have a raindrop with radius r equals 1.5 millimeters, falls from a cloud that is at a height h equals 1,200 meters above the ground. The drag coefficient c for the drop is 0.6. Assume that the drop is spherical throughout its fall. The density of water is 1,000 kilograms per meter cubed, and the density of air is 1.2 kilograms per meter cubed. As table 6-1 indicates, the raindrop reaches terminal speed after just falling a few meters. What is the terminal speed? And then B, what would the drop speed be just before impact if there was no drag force? So remember, with terminal speed, that's when our drag force is equal to the force of gravity. So that'll be how we're going to approach part A. So let's write down our givens first. Now we know that the radius of the raindrop is 1.5 millimeters, but of course we do not use millimeters in physics, we use meters. So there are 1,000 millimeters in 1 meter. Remember, milli means 1,000. So we're going to divide 1.5 by 1,000, and we get 0.0015 meters for our radius. Next, we know that the height is 1,200, so that means our initial y position is 1,200 meters. Our final y for part B will be 0 if it's hitting the ground. The drag coefficient c for the drop, c is 0.6. And then we want to assume that the drop is spherical throughout its fall, and they give us the density of water and the density of air, which is interesting. So the density of water is equal to 1,000 kilograms per meters cubed. And the density of air is equal to 1.2 kilograms per meters cubed. So a lot of information here. Now again, for part A, we know that we want to find the terminal velocity. So remember, terminal velocity is equal when the drag force is equal to that force of gravity. So I actually gave you an equation for terminal velocity in that PowerPoint for drag force, and that was terminal velocity is equal to the square root of 2 times the force of gravity divided by that drag coefficient times the density times the area. Now, with this terminal velocity equation, we know force of gravity is just going to be mass times acceleration of gravity, but interesting, we're not given mass. All right, we're not given mass, but we can find it. Okay. Also, we're given C, we're given the density, but we're given 2 densities here. Now remember, in this equation here, this density is going to be the density of the fluid that the object is flowing through. So this density will be the density of air, not the density of water. So there's another reason they give us the density of water. Okay, and then the area, the cross-sectional area of that raindrop, which we're given the radius, so that's going to be easy to find, okay? Which is why they give us the radius. So first and foremost, let's worry about finding the area and finding the mass, because we know that for force of gravity here, that's mass times acceleration of gravity. So we need to find that mass. Now, the reason that they give us the density of water is because density is equal to mass divided by volume. So that tells us that mass of the raindrop will be the density of the raindrop times the volume of the raindrop. Now we are assuming that this raindrop is spherical, like they said. So that means we're going to have the density of the water times 4/3 pi r cubed. So if you don't remember that, that's something you can look up. Also on the AP test, the volume of a sphere should be on the equation sheet. There's a bunch of constants like that. They have like the volume or the equation for area, the equation for, the volume of a sphere, the equation for the circumference of a circle, things like that. So we know density of water. We know our radius, so now we can plug in our numbers here. So we get mass is equal to the density of the water, which is 1,000 kilograms divided by meters cubed. And then that times 4/3 pi And then R here, remember, was our 0.0015 meters. And then we're cubing that. All right. So I'm cubing this, that's already in my calculator, which is nice, times pi times 4 divided by 3 times 1,000, and we get 1.41 times 10 to the negative fifth for our mass. And this makes sense because it's a very, very small raindrop, right? So it's going to have a very, very small mass in kilograms. Now we know the mass. We also want to find the area. So the area of a circle is going to be pi r squared. So this will be pi times r, 0.0015 meters squared. And we get 7.07 times 10 to the negative 6. All right. And that is meters squared. And then now we can finally plug in all of our stuff. So we get the velocity, the what's it called? Oh my God, I lost my train of thought. That terminal velocity is equal to the square root of 2 times the force of gravity, which is mass, 1.41 times 10 to the negative fifth kilograms, times acceleration of gravity, 9.8 meters per second squared, divided by force of gravity divided by c, which was 0.6, times the density of the air, which was 1.2 kilograms per meters cubed, times the area, which we found to be 7.07 times 10 to the negative 6 meters squared. So all of that, 2 times 1.41 times 10 to the negative fifth times 9.8, 0.6 times 1.2 times 7.07 times 10 to the negative 6, square root of all of this, and we end up getting velocity is equal to 7.4 meters per second. And that's our terminal velocity. I put V final. This should be VT, as in terminal velocity. Now for part B here, we want to find the final velocity as the raindrop hits the ground if that raindrop did not have any drag force on it. So we know that the initial Y position was that 1,200 meters. Final Y position will be the ground. Acceleration of the raindrop will be a negative 9.8 meters per second squared. And the initial velocity will be 0 because it's dropping from rest in the sky. So with all this information, we can use our final velocity squared is equal to initial velocity squared plus 2 times acceleration times delta x, or delta y in this case. So we get final velocity is equal to 0, and I'm square rooting both sides, so we get the answer, plus 2 times a negative 9.8 meters per second squared times a negative 1,200 meters. So 2 times 9.8 times 1,200, take the square root of that, and we get that the final velocity without air drag would be 153.36 meters per second. Now that is a very large final velocity, so that raindrop would really hurt if it hit your head. So thank goodness for air drag.